Our speaker today is Rigo Florez from the Citadel. Rigo, the floor is yours.
Okay, Sandra, thank you very much. I think 3 years ago, I went to New York in person, right, to talk about Metroids.
Yeah.
And but today I'm not going to talk about Metroids. I'm going to talk about something about enumeration. There's other area that I like a lot. Instead to have just one theorem and prove the theorem and give the background of the theorem, I'm just going to give a talk, like a motivating talk, to see how can we move through this area of research and show several results and connections with other areas of combinatorics. So this is in collaboration with Eva Czabarka from here, South Carolina, University of South Carolina, my previous institution. The other is with José Luis. He is in Colombia. I'm from Colombia, by the way. And Leandro Junes, that is in Pennsylvania. So here, this is Leandro, José Luis, and Eva. And the other area that also I like a lot is the elementary number theory, Fibonacci numbers. And I think we all know about Fibonacci numbers. Is a second order recursive sequence, and just combine the two previous numbers to obtain the next. So now, what is a Dyck word? A Dyck word is a word in the XY alphabet, only 2 letters. But we have a special condition is that here is, we need the same number of X and same number of Ys in the word. So in this case, we have 3X and 3Ys. And in this part, we have how many? 4X and 4Ys. But the special condition is that any initial word should not have more Ys than X. Here we are safe. Here also safe because no more Ys than X. And here is just the same number. And this is not good because in this part, yes, no more Ys than X. Good, no more Ys than X. But in this part, more Ys than X. So this is not a Dyck word. That is a bad Dyck word. So there are a lot, I think thousands of papers in Dyck words. And let's see another representation of Dyck words. Some people, here we are going to talk about the length. And we say this length is 8, but in reality, because we know that the length is actually 4X and 4Ys, we are not going to talk about any more 8. We are going to talk about the semi-length is 4. So from now, instead to say, oh, the length is 2 times 4, 2 times 4, we are going to say just 4, the semi-length, because automatically we understand that means is twice. And here we have all possible Dyck words of semi-length 4. And we have 14. And 14 is actually a special number, very important number. We don't know yet what is that important number, but it's important. And some people, they prefer, instead to work with Dyck words, they prefer to work with a balanced parenthesis. And then instead to work with this, they do the analysis on balanced parenthesis. And then there is another representation of Dyck words, and we call that one Dyck path. And Dyck path is we convert every X into northeast steps, and every Y into southeast steps. And suppose that we are in an XY plane. So this is XY plane, like this. And then in that XY plane, the Dyck word is starting at the origin and ending on the X-axis. So that is a very important characteristic of Dyck words. But now we are going to say Dyck path. right? Because now it's a path. So no anymore Dyck words. Now we are going to talk all the times Dyck path, because that's our interest. We used to work more on the representation. Here is, you remember the 14 representations of length 4. When I say length 4 means semi-length, right? And this representation, see here, is this triangle. But you know what? This triangle is, from now, we are going to call that pyramid. So we have this. This is the representation here. This is the other. We have other, and so on. So we have 14 Dyck paths represented in the way that we showed you before. So there is another representation of our Dyck words or Dyck path. So far we have 3. One is balanced parentheses, the other is path, and now we are going to have representations on binary trees. So binary trees. How to do the representations using binary trees? We are going to say, okay, the origin is, on the x-axis is basically the root of the tree. So, and every north is a step, is just a step down to the left, which is a link, and other, so again to the left, and then left here. But when you are going to down here, because it's binary tree, we are here at this point, we go to the previous vertex and we ask, is this already binary? 2 descendants? And if the answer is no, so we construct this link. Okay, for this other, so we are here and we ask, go to the previous here, and we say, is this binary? Oh, yes, then they go to here. And then this, we go down, this part, and down. So we are here, and then we are going up, but up is just a link to the left, and we put here the link to the left. So we put this here to the left, and then up, down, and then down, and down we say, okay, down we go, we are here, go to the previous, is binary? No, go here, put this, and then the last one, you say, okay, go to the previous, here, busy, go to the previous, busy, go to the previous, here, then put this here. And that is the representation using trees of a Dyck path. So some people prefer to work trees instead to what? To Dyck path. So it depends on the question also. So let me show you something here. Here is, this is representation of this, of this, this, of this. Some people can see other things that is not possible to see in this part. For example, if you see this pyramid is this tree, let me clean this too. This tree, this pyramid is this tree, and then this other is a sequence of pyramids and is in this form, right? If you observe, there is a kind of symmetry in between this and this, right? And you don't see that symmetry here. Or there is a symmetry in between this and this. So that is the reason when you work in one representation or the other representation, you can find different results. So it depends on what you are looking for. Okay, now we have several ways to work Dyck path. And you remember the number that I gave you before, the 14? 14 that is here is basically coming from this recursive sequence and is a Catalan number. So Dyck path is counted by Catalan numbers. So that makes now a famous Dyck path, right? Because Catalan is now famous. Okay, for our research, we are interested. We can ask many questions, but now we are going to narrow the question and just focus focus on some few questions, right? One is, let's introduce first what is a peak. A peak is subpath that is up and down. So, or you can say X and Y, and a value, or you can say in calculus is a local maximum, just the vertex. The vertex is the local maximum, but the peak is this subpath. Sometimes we don't distinguish in between that two, because counting this or counting the vertex is the same. This is the valley or local minimum, and valleys and peaks. And a pyramid, here we have one pyramid, we have another pyramid and another pyramid, but in our work, we are only interested in the biggest one, and we call the maximal pyramid. And here we have others. And the next is, what type of questions can we ask here? So, because we are interested to work in Dyck path is a lot of work, but we discovered, no, we didn't discover, we discovered a paper, right, in which they work at this path, and this path is special in one sense. If you go the height of the valleys here, this is 1, and this is 3. So if you organize from left to right the height of the valleys, you see that they are organized in non-decreasing order. And in that case, we call this one non-decreasing Dyck path. And that's what we are going to focus our attention in this talk. So we are going to work all the times in non-decreasing Dyck path. And this is give us, I mean, a lot of nice sequence, and that sequence are related with Fibonacci numbers. That is the reason why we, at the beginning, start interested on this path. So let's see here what happened with this. Here we have length 8, but remember we say just 4. How many non-decreasing Dyck paths are there of length 8? You remember that the Dyck path, normal Dyck path, it was 14, right? But just non-decreasing, we can count. We say 5, 5, and 13. So, but 13 is actually a Fibonacci number. So the previous was counted by Catalan number, but non-decreasing, it looks that is counted by Fibonacci numbers. Let's see if that is true. And then in 1987, Barcucci and al. They proved that yes, in fact, the non-decreasing Dyck path is counted by Fibonacci numbers. So we are going to keep this in mind, the Fibonacci numbers. But let's see here what kind of question we can ask here. So question that we can ask here is, for example, how many peaks are there? And this Dyck path, we say 1, 2, 3, 4, 5, 6, but it's not interested in one path. We are interested in all paths of the same length, right? So how many peaks are there in given a length? Let's say length 10. How many peaks are there in all that path? Maybe other question that we can ask is how many valleys are there? Or maybe other question is what? The height of the peaks. So what is the height of our peaks? Or we can add all of them, or the height of valleys, right? We can do many questions, or maybe the area of each pyramid, right? There are many questions that we ask here. And now let's just focus on the total number of peaks that are there. This is the length, what? 8. So length 8. I'm going to say 4, right? Semi-length 4. So how many peaks are there? And we count 1, 2, 3, 4, 5, 6, 7, and we obtain what? 32 peaks. But that 32 is actually a linear combination of Fibonacci numbers. You see, Fibonacci numbers again, and it looks that many times the Fibonacci numbers appears here in this type of path. I mean, non-decreasing, right? Decreasing, a normal path is different, but non-decreasing has a very good behavior. So the question is how to count. Let's go back. How to count the number of peaks? It looks that even for length 4, semi-length 4, it looks complicated to count that. Why? Because how we see here is not well organized. So if we organize that, maybe we can find an easy way to count the total number of peaks. And let me show you how to prove this, right? That in fact, that is the total number of peaks in non-decreasing Dyck path. Okay, what we are going to do is try to create a recursive relation or recursive function. So what we are going to do is we are going to collect all paths that the first part of the path is a pyramid of height 1. You see, all of them are of height 1. Then we have all pyramids that the height is 2. And then what? 3, and so on. And we observe this part, the tail of the path, is again a non-decreasing Dyck path. This is again non-decreasing, 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 non-decreasing. So basically, how is the construction of all of this? Is basically you take all non-decreasing Dyck paths of length L-1, right? All the non-decreasing Dyck path or length -1, and you put what? A pyramid to the path. That is, and same thing here. All non-decreasing length L-2, and you put a pyramid of this height, and so on. Okay, the other decomposition is the paths that they don't have any pyramid at the beginning. I mean, you don't have any what? Valley at the ground level. So this is without valleys at the ground level. Nothing, nothing. So what can we do? We observe here that this step and this step, this step, this step can be removed. And if we remove that, basically we have here what? Again, non-decreasing Dyck path, non-decreasing, 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 and non-decreasing. So using that technique, let me show you here. What we are going to do is, we call all of this, right, that doesn't have values at the ground level, we call that one Bn. But Bn can be sent under bijection, this is the bijection, to Dn-1. So instead to count the number of peaks here, we can count that here. It's the same, right? Because it's a bijection. So what we are going to do is create a function that we call Pn, and that's going to count the total number of peaks in Dn. So the total number of peaks here in Bn is actually the total number of peaks in Dn-1. So we say, okay, how many peaks are there here? You say, oh, Pn-1. Okay, perfect. But now we have to count the others, right? Let's go to Pn. So let's count the others. So for this part, basically to count the peaks here, we count all peaks in this part, all peaks here. But all peaks here are counted by the total number of peaks in Dn-1. So how many peaks are here? Is Pn-1. But see here, we are missing one peak. This. But the total number of peaks in this set is actually equal to the number of paths in this part. So basically in this part, we have a plus the cardinality of Dn-1. But we know the cardinality of this because this is what? A Fibonacci number. We say this is Fibonacci number 2 and minus 1 minus 1. So we have the total number of peaks here. We do the same for the total numbers of peaks here and the total number of peaks here. So what we have is basically this. Oh, what we did here. Okay, what we have here is, what is that? Pn is my recursive function, is all number of peaks here, all numbers given by the tails, and all numbers given by the first pyramid. And this gives us this recursive relation. And this recursive relation produces the Fibonacci formula that I showed you before. So, but that's basically what we are doing in this research. All the times we are constructing the recursive relation and then convert that one into something that is known, like a Fibonacci or something. Okay, that is the proof and how we construct all the total number of peaks in non-decreasing Dyck path. That is one way. The other way to count this that people in combinatorics like to do is using generating functions. Okay, let's do the same counting, but now using generating functions. The difference in between this proof is that in this proof we use a previous result by Barcucci, right? In generating functions, we can construct both the number of paths and the number of peaks in just in one generating function. Let's see how that works. So this is the family of non-decreasing Dyck path of semi-length n or length to n. And we are going to put here D to represent the cardinality of that set. And we are going to use some other parameters like the length of the path to introduce the generating function. And then we construct the generating function. So what is that generating function? Is fx, and is what? From 1 to infinity. And we are going to count p is a path that is a semi-length n, and we put here that. So let's see how, so basically all of this together give us what? The length of the total number of non-decreasing Dyck path and the n. Let's see one example of that. Okay, what is that? If n is equal to 1, so semi-length 1, length 2, we say is 1. When n is equal to 2, we have 1 and 2, and then you say 1 and another 1, you obtain, okay, 2, right, equal to 2. And if its length is 3, we obtain 5, and so on. So this is the generating function. But wait a moment. Here we were talking only about what? The number of non-decreasing Dyck path. And this generating function is actually a bivariate. I mean, 2 variables, right? So that means we are counting more than I promised you. Okay, let's see here. So this is the semi-length. And then this part is the total number of peaks. So now we introduce a new variable and new parameter to count. So this is going to count the total number of peaks in a non-decreasing Dyck path. And that generative function is here. When we evaluate that generative function, y equal to 1, we obtain the generating function that count the total numbers of non-decreasing Dyck path. But let's see how is the proof of that. So the proof of this, let's have again the decomposition of the path here. And remember that one path can be decomposed in this way. You have a path here, and you put 2 legs here. So in this case, is the path that doesn't have values at the ground level. And the other decomposition is you have one pyramid at the beginning of the path and then a path at the end. That is how we decompose this to create the generating function. And to avoid working with the empty path, we put just one pyramid of height 1. Okay, let's see here. So let's define my generating function. This is the generating function that counts the total number of paths and at the same time counts the total number of peaks. Okay, let's see how is that generating function. So we are going to say x is the contribution to the length of the path, and y is the contribution to number of peaks. Let's see here. In this case, the path is length 1, right? And the number of peaks here is 1. So we say x correspond to the length and y correspond to the peaks. So 1 peak, 1 length. And in this part, when you put this leg here, these two legs doesn't contribute to the number of peaks. So we don't put any y, just x. So this x correspond to this length. So length is increased by 1. And then this part is counted again by the generating function. So this corresponds to this part. I have the generating function, and this corresponds to this. Now, how we count this? So again, this is the number of peaks and the length. There is no any contribution to every contribution of the length is counted by this here. But let's see how is in this part. What is the nature of this? Maybe it's just a pyramid and a path. So that is x. Plus maybe what? A pyramid of height 2. And you say, okay, x squared because it's contributing of semi-length 2. Or maybe what? Height 3, 1, 2, 3, 1, 2, 3, plus x3, and so on. You can go to infinity. And in that case, you say, okay, the total number of this type of pyramid and with this path is counted by this series, right? And then how many, this is the geometric series, by the way, and how many peaks? Only one peak, we say 1, and one fixed length is x. So the geometric series and one path and one length produce this times all paths here. So that we have the generating function. And this generating function, when you solve for x, for this, right? When you solve for this, you obtain the generating function that I showed you before. And that generating function counts both the number of peaks and the number of paths and non-decreasing Dyck path. Okay, any other proof that we do here? I'm not going to do proof more, right? But any other, when we say generating function is basically using this type of decomposition for the generating functions. And we do similar counting. Okay, now we are going to show you more connections. Now it's only, the rest of this talk is only show you connections with non-decreasing Dyck paths and other areas of a combinatorics. So first of all, we define what is a polyomino. A polyomino is a set of squares such that when you check the bound of that square, the bound does not intersect itself. So don't do this like this, right? So that is a polyomino. In this area, sometimes it's very hard to find results. It's very complicated. They express in this, they work very hard to find results. But in our case, we are going to find a connection in between these polyominoes and a non-decreasing Dyck path. let's see how is that connection. Okay, first of all, let's define one special type of polyominoes, and we call that one Cullen-Convex. Cullen-Convex means is a polyomino such that when you have a vertical line, the vertical line is totally contained within the polyomino. You see, this is Cullen-Convex, and the other is directed. Directed means when you go from the lowest point on the left, you can go wherever you want using only vertical or horizontal steps. So you can go wherever you want here, or you can go from here to here to here to here if you want. And that is directed Cullen-Convex polyominoes. So look at this. This is not directed because if you are here, you can reach this point. You can't. And it's not Cullen-Convex because this is not totally within the polyomino. So this is not good. This is good. And this is only Cullen-Convex, but it's not directed because you cannot go here. So only this is the good one. So the question is, we have very nice behavior with this DCC. And the question is, how many are there? Okay, let's see here. If we have one square, how many DCC polyominoes can we construct? Obviously, one. But if we have two squares, we can construct two. If we have three, 1, 2, 3, 1, 2, 3, we can construct 5. If you observe, this is basically what? Fibonacci numbers. If you observe the formula, is the same Fibonacci number that count the total number of non-decreasing Dyck paths. So it was proved in 1997 by Barkushi, the same person who discovered the non-decreasing Dyck path. But it was only 5 years later that other people discovered that the relationship in between DCC polyominoes and non-decreasing Dyck path. It was no Barkushi. It was Prodinger and Deutsch. So what they did is they defined the polyomino DCC, and they say, okay, look, this is the level 0 here, put level 1, level 2, level 3, level 4, 5, and 6. And then we are going to see what is the relationship with these levels and the non-decreasing Dyck path. So we start with level 0. Level 0 means origin, and go to level 4 here. You go here. Then from level 4, you go to level 1, and then from level 1 to level 3, and so on. And that way we have a bijective of that. See here. So let's see. Here we are in level 5, maybe it's this, and then go here, and then go here, and here. Now we have a bijective in between DCC polyominoes and non-decreasing Dyck path. And that is good for one reason, because sometimes find result in this part is hard, but maybe is more workable here. And because we have a bijective, something that we can do here help us to understand better this. So one the first thought is maybe quite obvious, is if you see here the number of peaks, how we construct a peak. So we go from level 1 to here to level 0. So the level 0 to level 1, right? So this and this. So it means we have one peak and we have one column. So we go from here to here, and then from here to here, and we have another peak and another peak. So that means for every peak that we have here, we have one column here. So the number of peaks here is actually equal to the number of columns in DCC. And you remember the result? Yeah, I'm expecting you remember the result, all results here. But okay, this is the number that we showed before, the number of peaks. And this number is 10, and I'm going to show you that here. So 10 is number of columns here is actually equal to the number of peaks. Now, another connection. Yeah, I told you from the beginning that here we are going to show you a motivation, several areas to work. And let's work now non-decreasing path and reorder arrays. So let's first talk about primitive path. So primitive path is all path. I talked to this before, but this is all path that they don't have what? Any valley at the ground level. So no valleys at the ground level. And we know how to count this, because basically is if you take this out, we can count that counting the number of non-decreasing path of semi-length dn minus 1. Okay, that is not hard to count, is this formula. But the important is the connection of this and the other area of mathematics, combinatorics in particular. Look at it. This is a normal Dyck path, right? And this normal Dyck path, you can write this normal Dyck path as one primitive path, other primitive path, other, and this. So this path can be written as a concatenation of 4 primitive paths, but this is just the regular Dyck path, right? This is the regular Dyck path. It's a concatenation of 4 primitive paths. The question is here, the same question is, now let's go back to non-decreasing. And in this part, we ask, okay, how many of these is just one primitive path, only one primitive path? And we say, okay, 1, 2, 3, 4, 5. I don't see more. Okay, now the next is how many of these are concatenation of 2? So let's see here, 2. 1, 2, 3. I don't see more, right? Only 3. So how many of these? Oh, wait a moment. 4. Maybe another. I don't see other. Do you see other? I don't see more. Okay, let's see. Let me change the color here. How many of 3? 1, 2, 3. 1, 2, 3. And 1 of 4. So the question is, how can we count, right? How many non-decreasing paths are just primitive like this, right? No valleys at the ground level. Or how many with one valley, I mean, 2 primitives, right? 1, 2, 1, 2, can be counted here. So we use the same idea of the decomposition that we had before, and we see this. We organize here with one primitive path is 5, 2 primitive paths 4, 3 primitive paths 3, 1, 2, 3, and 4. 1, 2, 3, 4. Yes, is 1. Okay, we answer this using the generating functions. Here is the generating function. How is the construction of the generating function? Just working with a similar decomposition, we obtain the generating function, and then we obtain I'm going to say this is closed formula, but this is not quite correct. This is just using binomial and Fibonacci. Okay, now there is a relationship in between this type of path, I mean, this type of counting, and reorder array. Okay, let's see what is reorder array. So we all are familiar with Pascal triangle, right? Pascal triangle. And what is a reorder array? Is a generalization of Pascal triangle. That is basically a reorder array. Pascal triangle is a special case of reorder array. Okay, what we are going to do is we are going to distinguish in between two parts of reorder array. We are going to say that this is the internal part, this is the inner part, and we are going to call this one external column. And the idea is how to construct this. We are going to use a recursive function or relation. So you pick, no matter what, any sequence here of numbers, but we need one condition. The condition is that the first entry cannot be 0. The other is what? This is infinite. The other can be numbers, right? And another sequence, and no conditions on the first, just numbers. And how to construct that? Any. I brought here this green. How to construct this green that is internal, right? This is internal. When this is internal, to construct the green, you go to the previous, this, and take this vector. Look at this. Think this infinite vector goes to infinite. Take the number and multiply under that product with this. So basically you say what? The first here, the second here, the third here, and when you combine all of them, you obtain the green. So for the external, this is the step. You are going to construct the red. How you do the red? You take the second sequence and take the previous. See, in this case, you went diagonal. Here you go straight up. So you multiply the first with this, second with this, third with this, and so on. And then when you combine all of that, you obtain this square. Let's see one example, how that works. So I'm gonna pick my A, just 1, 1, and the remaining what? Zeros, satisfy the condition. And my Z is what? 1, 1, 1, 1, 1 to infinity. So what we are going to do, we are going to construct 11. So what is 11? 11 is, you go to the previous, 7, 4, and 1, right? And you do this, 7 times 1, 4 times 1, and 1 times 0. And you combine. So that is what? 7 and 4 is 11. And in that way, you can construct all of them. It's the same, right? So what is the construction of this? Let me clean this. This. So we are going to construct this 13. And what we do is take the previous, all of this, and you multiply the first, second, third, and so on. And then you combine. So 5, 4, 3, and 1, that is 13. That is how we construct the reorder arrays. And this is identical, a little bit more general, actually general, of Pascal triangle. That is the same idea. That is one way to construct the reorder array. That is using recursive relations and using a sequence. But there is another way to construct reorder arrays. Let me show you here. One is you have one generating function and you have a second generating function. And we need the special conditions. When you evaluate this generating function at 0, G0 cannot be 0. And this, when you evaluate that as 0, must be 0. And in that way, you are going to construct all columns. This is correspond to the first column when you have power 1, second column, third columns, and the other column. Let me show you with more details here. Give me 1 second. This is the definition. Let's see here. Back, down, down. Okay, look at this. This is when you do this product, you obtain this generating function, and you take the coefficients here. When you do this product, we have the generating function with that coefficient, and the coefficients are here. So that is how we construct the reordinal array using generating functions. So let me go back here. So if you observe here, and in this part we have the f that we require to construct the reordinal array, and here we have the g that we require to construct the reordinal array with extra x. This extra x is not a big problem. The only problem is that you shift the result a little bit to the right, but that's the only problem. And here we have the formula that counts the total number of paths that can be written as primitive path. Depends, right? K primitive path. Let's go down here. Down more. Okay, look at this. In this part, how many paths of length 4? This is length 4. 1, 2, 3, 4. Length 4 can be written as a concatenation of just one primitive path, 5. How many of them can be written as a concatenation of 2? 2 is 4. How many of 3? 3. And how many with 4? 1. And in that way, we see the relationship in between reordinal arrays and non-decreasing Dyck path. Similarly, I think Sandra, how long? I think it's almost time, right?
You have about 10 minutes more.
Okay, 10 minutes. Okay, I thought it was only 15 minutes, but I have more time. I can keep talking. Okay, what happened with this? Look at this. This is what we know, the result, to count the number of paths. That is a concatenation of k primitive paths. But what is interesting of this in the reordinal arrays? So in this part, you remember that this is counting the same. But now let's go here. You remember that we construct 11 using this and this. And we say, okay, look, this is here. But now we have an identity, because since this part that is in this spot can be written as an addition of the two previous, we have this identity. So for this part, and similarly for this here. So reordinal arrays also can help us to extend a little bit in more identities for some result that we have found in using a non-decreasing Dyck path. Okay, this is very fast. Another idea is, if we have pyramids and we just check the height 1, height 2, height 1, we call this the weight of the pyramid. And I'm not going to go to details of this. Just go here, and we are going to say, okay, how many pyramids are there of height 1 at the ground level? And that is counted by 13. So this is height 1, right? And how many are there of height 2? 1, 2, 2, 2, 2. We see that there are 5, another Fibonacci number. And how many of height 3? You see height 3. 1, 2, 3. 1, 2, another Fibonacci number. And here height 4, height 4 is only 1. Again, Fibonacci number. So the formula is given by this, with by this generating function, but there's also counting by the reordinal arrays. And let's see, 51. Yeah, I think I can keep talking. Okay, another connection. You see, in this part is just motivation to see how many connections we have with other areas of mathematics. So Asoli, she in 2018 in her PhD thesis, she defined in a word in a certain alphabet in this alphabet is using from 1 to 5, and she defined a peak in this alphabet, right? And this word, a peak is, this is peak if the two previous are less than this. So 5 is a peak because the two previous are less than this. 4 is a peak because the previous and after, it's a two previous. The previous and after, right, are less than this. So again, these two less than this, these two less than this, and these two less than this. That is a peak. So, but she went further than that, and she said, okay, this is symmetric if the two are the same. So this is symmetric because these two are the same. This is symmetric because these two are the same. But this is not symmetric because these two are not the same. So here she calls this one what? Asymmetric, symmetric peak, symmetric peak. So we read the result and we say, okay, because we are working with peaks, how can we extend that concept to non-decreasing Dyck path? And later we realize, hey, wait a moment, that result does not exist yet in just Dyck path. And we proved this for Dyck path, and later we proved that for non-decreasing. Yeah, because for Dyck is much better because it's more general. So what we did, we say, okay, we had this pyramid containing the peak. And we say, okay, this peak is symmetric if the two values at the leg of the pyramid are the same height. So symmetric, this peak is symmetric because these two values are the same level. Symmetric, symmetric, symmetric is symmetric. This is not symmetric because let's suppose this is a valley, right? And this, they are not at the same level. This and this, they are not at the same level. This and this, not the same level. So this is non-symmetric. So we define this and we prove that the total number, right, the recursive relation to count the total number of symmetric peaks is given by this recursive relation. Quite crazy, yes. But this is Catalan number, and this is the recursive relation here inside. And then we also use that recursive relation to count the total number of symmetric peaks of a given length. And in this case, the length is 4. And then we count and we see that in this case, the greens is equal to 23. And also we have found the generating function, which is here. And I think that's it. That's everything they have to tell you today.
Let's thank the speaker. And stop the recording and we can ask questions.